In this next application of integration, we're going to be able to compute the length of a curve between a particular starting place and an ending place. So we're really asking the question of how can we compute the arc length of a curve in general? So just to build up this question would be, we have some function f of x. And what we're interested in is asking, what is the length of this curve, say between some starting place, x equals a, to some ending place, x equals b. So what is the length of this part? And you might be wondering, what are some of the applications of this? Well, actually computing the length of a curve is actually a really popular thing in computer graphics and a whole lot of other types of applications that you may not even be thinking of. So beyond computer graphics, even to computer typography or the font or the way we design fonts for computers, people use arc length type computations. But for us, what we're going to do in class is start by deriving the general formula for arc length. That's right, we're going to compute and derive a completely general formula for the arc length of a curve. And where this is going to start is with an idea from geometry, the distance formula. So if you remember, the distance formula between 2 points is equal to, well, the sum of the difference of the x and y values between those points. So we have the difference between the x values, the difference between the y values, and we square those. So maybe I should just draw this out. So for example, if we just have 2 points in our plane, we have point 1, which is x1, x2, or sorry, x1, y1. And we have point 2, say x2, y2. What the distance formula gives us is the exact linear distance between those 2 points that we're just calling d. So for us, when we're deriving this formula, if we revisit this idea for the distance between curves, we can think through the following scenarios. And I get really excited about this unit because I think a lot of the ideas we get to explore here come up from Riemann sums. We get to blend that with ideas from the distance formula and reintroduce some ideas like limits from calculus to build up this formula with an integral in it. So for example, if we have this curve and we're interested in the length of this curve between A and B, well, one thing we could try to do is, well, we could just approximate the distance of this entire blue line by just taking the distance between these 2 points. But you know what might be better than this approximation of just computing the distance between 2 points? What if we threw another point in the mix and then computed the distance between these pairs of points? And said that might be a good approximation if we just add together D1 and D2 here. But you know it's better than just adding together 2 line segments? What if, yeah, we add together, instead of 2, we add together 3 line segments? And you might see where we're going. The more line segments we start adding together, so adding the distance D1, D2, D3 here, we're going to get better and better approximations to the length of that curve between A and B. And this is really where we get to start introducing some of these ideas from calculus. So instead of just, say, 3 line segments, if we start really going crazy and putting in 10, 20, 1,000, 1,000,000, or in calculus, we're allowed to take limits, and taking that limit as the number of line segments or distances between points that we calculate goes towards infinity. And that's going to pop out at us using this distance formula, a very nice formula for the arc length of any curve.